Today I'll be telling you about the modeling and analysis of EHV long AC uncompensated transmission line. It is the topic of Unit 2 of the subject PQF. So the lecture will basically discuss about the model and the analysis of EHV AC long uncompensated transmission line. We'll first study how to model the lossy transmission line and a lossless transmission line, and then we'll proceed for the analysis of this lossless line. Okay, there can be two conditions, unity power factor load and the symmetrical line with unity power factor load. And from this, we'll derive the midpoint compensation method. So basically, if we talk of the lossy EHV AC uncompensated transmission line, the Thevenin network can be shown like this. And for this particular transmission line, if I talk of a distance x from this particular point to the receiving end, this dx distance will be there from this point to the sending end. So basically we are modeling the transmission line from the sending end to the receiving end, and we are taking the distance to be x plus dx. So the current Ix plus dx will be given by this equation, and the voltage for x plus dx distance, that is the sending end voltage, will be given by the second equation. You will apply KCL for determining Ix plus dx. So Ix plus dx at this point, if you apply KCL, Ix plus dx will be equal to the sum of these two outgoing currents. And this current will be Ix, this one, and this current will be the voltage, that is Vx plus dx, multiplied by the particular admittance, that is Ydx. Similarly, if you apply KVL in this particular loop, so Vx plus dx you will get as Vx plus this particular drop, Zdx. This is Vx. So this whole drop is encountered here for this Vx, and plus this Zdx into the current Ix. So where I am taking the lossy line, so that means the resistance and the conductance are taken into account. If you differentiate both these equations, dV by dx and di by dx, find them out, it will be equal to Z into I, and di by dx will be equal to y into v. Now double differentiate it. So you will get dv by dx equal to z into di by dx, and replace this di by dx by yv. So zyv. Similarly for this equation, now solve this using partial differential equation method, and you know that when we solve it, the variable v will be equal to the sum of complementary function and particular integral. So since the particular integral will be 0, this will be d square v by dx square minus z by v equal to 0. So m square minus zy bracket closed out and outside bracket multiplied by v, it is equal to 0. So if you solve it, you will get only complementary function solution, and Vx will be a1 e to the power gamma x plus a2 e to the power minus gamma x, because the roots are equal and opposite, where gamma will be equal to square root of z into y. And if we see z is r plus j x, and if we see y is g plus jb. So it will also be a complex number. Let us define it by alpha plus j beta. Zc characteristic impedance will be this. If we solve Ix, this Zc will be given by square root of z by y. Similarly, if you find out the boundary conditions and you apply those boundary conditions on these two equations, Vx and Ix, you will get boundary condition. Let us say if x equal to 0. If x is 0, this particular sending end voltage will be equal to receiving end voltage, that is Vr. Put it in this equation, in this Vx equation, you will get this equation. Similarly, at x equal to 0, Is will be equal to Ir. Put it in this equation, you will get these two equations. Now there are two unknowns, A1 and A2. Find them out in terms of Vr and Ir. You will get the equations of Vs and Is at the distance x by these two equations. So this is the model. This is particularly the model of an uncompensated lossy transmission line, EHV line, where cos hyperbolic gamma x, as you know, will be given by these two equations, and sine hyperbolic gamma x. Similarly, if we model the lossless line, now the similar line is taken. So the previous model is defined here in terms of these two equations. Now find out if condition of a lossless line, what will be the condition? That the resistance and the conductance will be equal to 0. So gamma will be equal to j beta. It will be given by j omega under root LC. So the characteristic impedance will be given by this, and if you put these two values in the above model which you derived in the previous slide, you will get these equations. So when we talk of a special case, when VR is equal to Zn IR, the load resistance RL is equal to Zn, suppose. So Vx and Ix will be given by these two equations. And now substitute x equal to d. Let us say the total length of the transmission line is d. Substitute x equal to d in these two equations, and you will get the model of a lossless transmission line. So this is the model of a lossless transmission line. Now, if we talk of the two-port network model, basically what you have derived up till now is the model of a lossy line, and then you reformed it for the model of a lossless line. Now, what you do, you transform, you write this equation in terms of ABCD parameters. This is simple. These are two equations. You can write them in the form of matrices. So, VSIS, form one column vector here and take out the four coefficients of VR and IR. So, they will be represented by these four parameters ABCD. Write down their values. Now, condition which will follow here for a transmission line is D will be equal to A and AD minus BC equal to 1. So, these are some of the points you need to remember. And if you want to find out VR and IR, take the inverse of this above equations, above matrix, and find out VR and IR. This will be given by this equation. So, the two models or the model for the transmission line can be represented by Vs and Is in terms of these equations, or VRIR in terms of these equations. Now, if we talk of the analysis of these lines, we have modeled the lines, transmission line, and we have modeled it for lossless as well as lossy line. So, if you want to analyze it, there can be two conditions. With unity power factor load, we can make this Thevenin circuit. The phasor diagram will be like this. So, the two equations derived above are given here. The assumptions are Vs will be constant, VR will be varying with the load. Unity power factor load is taken, and the line is lossless. So open circuit voltage at the receiving end will be obtained from this particular equation, first equations. When you put IR equal to 0, open circuit voltage at the receiving end. So VTH, that is VR will be equal to Vs by cos theta. So here VR will be equal to Vs by cos theta as IR will be equal to 0. Now find out ZTH. How do you find out? By reducing all the sources equivalent to 0. So VR by IR, when Vs is equal to 0, you will find out from these two equations. It will be Zn tan theta J, imaginary part. So from the phasor diagram, you can see VR is equal to VTH cos del. So VTH is given by Vs by cos theta. Put it here, Vs by cos theta into cos del. Power flow in the line from this particular diagram will be given by VTH VR sin del upon Zn tan theta. Power flow in this particular diagram, Thevenin circuit. You have made now the Thevenin circuit. So VTH and VR will be equal to Vs. So equate them and write the equation. The maximum power can be found out when del equal to 45. So P max, put it here and you will be able to find out the value of P max, maximum power. At this value of power, the receiving end voltage will be given by this, and the no load, at no load, when suppose we are talking of no load, the load is open circuited. That means the power delivered to the load is 0. That means the open circuit voltage VRO will be Vs by cos theta as del will be equal to 0. So this will be excessive. This indicates the Faraday effect. And as theta increases, the receiving end voltage will be greater than Vs. From this equation you can see. And the charging current, if we say that the line is on no load, the sending end current will not be going towards the load. That means it will be giving you the, whatever current will be flowing in the line will be giving you the value of the charging current in the line. And this is given by this equation. The charging reactive power at no load will be given by QSO. It is the imaginary part of Vs ISO conjugate. So it will be given by putting, if you put the values of these two terms. And if we say that I analyze the line with symmetrical line and unity power factor load, both the conditions I have taken. So some of the assumptions increases that the line is symmetrical, therefore VSVR will be equal to V. Injected power I am assuming to be injected reactive power to be equal to minus QR. That means QS will be equal to minus QR. So if you find out the total power flow in this line, it will be given by this equation. Current flow on the line Vs minus VR cos theta by Jzn sin theta from the equivalent circuit we drew in the previous slide, like this. Okay. So if this is found out, Vs is now at an angle del, and V, because there is a load, so let us say the angle with the load is theta. So it will be V cos theta and divided by Jzn sin theta, because it was the equivalent resistance between the line. And if we talk of the total power from delivered to the load will be SR will be equal to PR plus JQR. So VR IR conjugate. So find out from the equations given above, VR and VS are equal to V. So put it equal to V and write the value of IR from this equation. Find out the power value, active power value from this particular equation, the real part of this particular equation. It will be given by V square sine del upon Zn sine theta. So term, if I take out the surge impedance loading from this equation, so the surge impedance load is defined by P subscript n, and it will be given by V square by Zn at the natural impedance or the characteristic impedance. So QR will be given by this equation, imaginary part, find it out, and it will be equal to minus QS from symmetry. Okay, and if you apply KVL, if you find out from these equations, you will be able to see that the voltage profile of the transmission line, when we talk of this is the transmission line sending end and this is the receiving end, the voltage profile reduces at the midpoint, the voltage is minimum. And if we talk of the load, let us say the load is equal to the surge impedance load, then the voltage profile does not vary much. But if the load on the line is greater than the surge impedance load, the voltage at midpoint is minimum. It reduces gradually from the sending end to midpoint, and then it increases gradually from midpoint to the receiving. Not a good profile. And similarly, if we talk of load when it is less than surge impedance loading, this profile is also not good. So I identify here that the midpoint is the susceptible point. I need to compensate the line at the midpoint. So if I want to find out the voltage and current at the midpoint, what you can do, apply KVL in this circuit from sending end to midpoint and from midpoint to receiving end. Two meshes are created and apply KVL. Here you will get these two equations. There are two equations, two unknown, Vm and Im. Find out, solve these two equations. Vm and Im will be given by these two equations. So if you see here Vm and Im, the conclusions are basically that as line length increases, voltage regulation and reactive power management is required. And voltage and power profile is very poor at the midpoint when we talk of the transmission lines greater than 500 kilometers. That is a long transmission line. So it is the ideal point for the compensation if it is to be provided at the transmission line. And the compensation, if provided at the load end, it will improve the power transfer capability as well as the voltage profile along the line. So you can see the total power at the midpoint of transmission line will be given by VMIM. You have found out these two values, multiply them, you will get this value. Now the no load voltage at the midpoint will be given when del equal to 0. So VMO will be V by cos theta by 2. And no load reactive power will be the charging reactive power. So QSO will be equal to minus QRO, because we are assuming that this is the symmetrical line. So this will be given by this equation. So this was all for this lecture. Now in the next lecture, we'll be discussing the next topic.